afternoon, Earth Science students. Please copy down this teaching point. I'll be able to describe how energy transforms from one form to another, such as from potential energy to kinetic energy, and analyze real world examples of energy transformations in systems. All right, launch for today. If you touch the sand and the water on a sunny day, which do you think would feel warmer and why? All right, so we have two pictures. We have a nice sunny day at the beach and a nice sunny day for this nice calm water. All right, hit the pause button, think of an answer, and when you have your answer, hit the play button and hear me out. All right, so with respect to these two surfaces, they will change temperature differently. All right, they will both increase in temperature. Yes, on a nice sunny day, both will increase in temperature. On a nice cool day, it will decrease in temperature. When the sun goes down, it's going to decrease in temperature. Both of these surfaces will. One's going to heat up faster and one's going to heat up slower. All right, so if you go on a nice sunny day at the beach, that sand is going to feel hot on your feet, right? The tips of your feet and the base of your feet. And the only way to remedy that situation of feeling hot during a hot summer day at the beach is to cool down in the water. And that water is definitely at a cooler temperature than the beach sand. All right, so our solid surfaces here, right, the sand will increase and decrease in temperatures a lot faster than water can. All right, here we go. Heat production, right? Transformations of heat energy often occur when there is friction. So an example of friction, right? If you take your hands, put them together, right? And you rub your hands together, right? You can feel the heat that can be generated between your fingertips, right? And that is called friction. There are many examples of heat transformation, but one is wind blowing over the ocean, creating waves and surface ocean currents. Right, at the interface of the atmosphere and hydrosphere, heat is formed. All right, the atmosphere is gases, right? Layers of gases. Hydrosphere is water, right? Water that's sitting on the solid surface of the earth. Mechanical energy. All right, mechanical energy, the total of the potential and kinetic energy of an object or system. Either Ke, kinetic energy, or Pe, potential energy, can be transformed into the other. A great example of this will be Kepler's second law of planetary motion. Right? So when you're at perihelion, the planet will revolve faster than aphelion when it's farthest away. So when it goes faster, we have higher kinetic energy, but we have lower potential energy in its place. As that planet moves away, kinetic energy will be decreasing, and then you would in turn then increase your potential energy, your stored energy of increasing velocity once again. All right, moving on, we have our wavelengths, right? Electromagnetic energy can be absorbed by an object and re-radiated at a longer wavelength. Now, this picture, we've seen this picture before. We have intensity of electromagnetic radiation. All right, our star, matter of fact, all stars give off a wide variety of electromagnetic radiation, from gamma rays to X rays to ultraviolet light to visible light to infrared to microwaves and to radio waves. All right, our sun, our star, gives off at least three that are pretty high. All right, the highest intensity would be visible light that our sun gives off, right? And our sun also gives off a lot of UV radiation, and it also gives off some infrared radiation. All right, so since most of these wavelengths are going to be UV invisible, which are shorter waves, our next longest wave would be infrared. So our Earth will absorb these shorter waves and give off infrared. All right, now what I need you to do is pause the screen, type in what is infrared radiation, and there should be one word that begins with an H. All right, pause it here, do the search, and when you're done with the search, hit play. All right, and that H word is going to be heat, right? And that's what helps maintain the Earth to have that beautiful average temperature of 15 degrees Celsius from North Pole to South Pole. All right, some definitions here. Temperature is the average kinetic energy of the particles of a body of matter. The temperature of an object or region is directly related to the amount of heat or thermal energy in the object or region. All right, so we're going to be dealing with weather conditions, and every region or every area has certain temperature characteristics that go along with them that we're going to help break down together as part of the air masses and how these air masses can interact with each other to give us our weather fronts. And the weather fronts is part of the NGSS standard. All right, when the thermal energy of one object is greater, it has a higher temperature than another object. All right, and differences in temperature can help make and create the movement of these air masses. All right, going back to our warmer for today, we have specific heat. All right, that definition is the quantity of heat needed to raise the temperature of 1 gram of a substance 1 degree Celsius. All right, and this is the chart that we had on the old reference table. All right, so specific heats of common materials. We have liquid water, of course, in the liquid phase. We have solid water, which is ice in your solid phase. We have water vapor, right? And vapor is going to be in its gaseous phase. All right, and we have specific heat. Now, specific heat is the amount of energy, right? Joules is energy. The amount of energy needed to raise 1 gram of this substance 1 degree Celsius. So, this is all based on these numbers. So, water has the highest specific heat in comparison to the ones that are listed here. All right, the lowest number that we have is lead, right? Lead is 0.13. So lead is the lowest amount of energy needed to raise 1 gram of lead 1 degree Celsius. Quite amazing. All right, so lead, copper, iron are all metals. And notice that these metals have lower specific heats. All the different phases of water have high, but liquid water, which is the majority of the Earth's surface in terms of 70% being water, hydrosphere, 4.18. And this number will help understand why certain areas of the world, depending on where you live, have warmer climates than other parts that have cooler or colder climates. All right. This is essential here, right? So for us living on Long Island, right, an island is surrounded by water, and because we're surrounded by water, um, that plays a major role in how the area heats up and cools off around us. So liquid water needs a lot more heat energy to raise it 1 degree Celsius, which makes water a cooler feature in comparison to, let's say, that beach sand. That beach sand can be really broken down pieces of granite as an example. Granite is the type of rock that makes up most of the continental crust, and that's at 0.79 joules per gram degree Celsius. So that's how much heat energy is needed to raise that 1 degree Celsius. All right, which is at a much lower value than liquid water. That's why our beaches heat up a lot faster, much faster than the liquid water. However, at nighttime, right, the land's going to cool down fast, but the water is going to cool down slowly. So that liquid water is able to retain that heat much better than the rocks of the continental crust. All right, that is the conclusion of this lesson, and I'm going to build into our first weather variable tomorrow with air temperature.